So this presentation is actually not a presentation, it should be an exhibition from Bob Bruner. Unfortunately, he could not come with us. That's why we converted it to a presentation, and some samples are sent here from Bob Bruner, so you can see them just after this. You can have a look at them. Bob Bruner is, since a very long time, is trying to put all the concepts and hypotheses about the origins of life in a small collection of very important minerals and meteorites. And this is actually, he made a story out of those. And this story of this mini version of exhibit of meteorites is presented here. And it is based on three conditions for life to start. One is the source of organic molecules, where they come from, these organic molecules. And one example is the Martian meteorite, as you have heard already. Then there must be a solvent somewhere. And water is one important that we know very well. And then the source of energy to power the start of life. This story around it and the whole theory has changed over the years. I try to say exactly what he wanted to transfer to us. I hope I can manage it very well. So he thinks that future research we need, and we all think about like this, that new research will reveal new sources of energy, new locations to start life, and of course, new theories. So the problem of finding the origins of life still has time and will be with us. The questions will be with us for quite long. I hope we can manage to have some signals from other planets like Mars, for example, that yes, we can find life also elsewhere than Earth. So this is the collection. Here you see two only of these minerals. This is the collection I have seen this collection several years ago, 2016 it was, when he brought these collections to Athens in Greece in a conference we organized there on astrobiology. And he also was so kind to give me a very nice collection of meteorites as a present, and Martian meteorites especially, which are now very rare meteorites. So this is the collection and includes minerals that are identified on planet Mars, important Martian meteorites, not all, but the most important ones, and other meteorites with organic content that is synthesized into nebula systems and in the proximity to stars. So this is the list of exhibition. So he has, if you go back, there are some numbers, these are numbered actually, but the abstracts contain this table. So you can follow this abstract and some links, I think that they are given there. So this is one of the sample is minerals that are formed, or rocks that are formed underwater to protect from impacts at these early times. Another sample is mineral formed on the surface of planets during wet and dry cycles, like you have heard in the previous talk. Then compartments inside crystalline minerals to form presence organic molecules, minerals that demonstrate these compartments. You have already heard from Helen a very detailed talk on this. And then very dry land to release boron to stabilize ribose in RNA. There was a paper on this actually several years ago. Or provide a method to transfer life from Mars to Earth. Meteorites are a medium for this. And also transfer water There are in this collection some meteorites again that can do this and demonstrate that such a thing could exist, and also provide a method to transfer phosphorus to a planet. And of course, some to protect and produce these wet-dry cycles that show that it can happen. So I picked some of these pictures of the collection and I show them here. So clays are very important minerals, as you have heard also with mica. They are the same structure actually. And of course, pumice, which has vesicular matrices. These both of them are very capable of keeping and also synthesizing, as you have heard, organics. Here you see modmorillonite and kaolinite as an example from this collection. And pumice is to demonstrate highly vesicular volcanic matrices, rocks, the natural rocks that we can collect very easily close to different volcanoes. Then we go to other minerals like olivine and pyroxene, and these are primary silicate rock-forming minerals of the upper mantle, actually, and they come with tectonic. With tectonics, they can come back, not back, but they can come to the surface of the Earth, and so we can see them and sample them. Also, there are other ways of they are coming back through volcanism, that they are coming like xenoliths. That's why we know the composition of mantle. Then you have here two examples, the serpentine example and magnetite example, that for bulb they represent the black smokers. No, sorry, the white smokers. So serpentine magnetite and sometimes brucite as well. Here down, and it's here down there. And black smokers are represented by pyrite, because in black smokers you have a lot of pyrite forming in the depths of the ocean. The mineral to represent dry land and also to offer boron for the stabilization of RNA is colemanite. This has been suggested, as I said, as a source for boron to be used to stabilize the ribose of RNA. So you could have seen also this mineral from very close if Bob could be with us. And also here you have three meteorites, three Martian, very important Martian meteorites, Nakla and Black Beauty and Tistent meteorites, which are very rare and difficult to acquire, actually. I have some in my collection because of Bob. And if life existed on Mars, these could be the vehicles to bring them to Earth. This is a theory which dates back to 2013, actually, especially for Martian meteorites. Then you heard already about geyserite. Here is a mineral, the geyserite mineral, which is a siliceous sinter, opal-like material forming encrustations around hot springs, exactly what you have heard already in the last talks. And close to it comes also opaline silica, which is about the same material, but this is a precious stone, because you see here some of these different kinds of opals. They can be transparent, or they can it's diffraction, actually, that on optical light that produces those colors here, because opals are actually microspheres periodically deposited, and they produce this photonic diffraction pattern that comes out to our eyes as different colors depending on the angle that you can see. Here is opaline silica, but if you just process it a little bit, you can see the very nice colors, and you can use it as a as a precious stone. This is identified also on Mars remotely, but also from meteorites, Martian meteorites. One of my works actually with colleague from Glasgow University also identified opal in Martian meteorite in Nakla. And now we have here a chart from the more recent theories about it. Is a silica gel actually deposits, a chart deposits as starting from a silica gel at the bottom of the oceans. And it's a very hard rock of sedimentary origin, micro to cryptocrystalline quartz. It's quartz, it's not amorphous like opal is. It's quartz, but microcrystalline to cryptocrystalline, and often is found to petrify organic matter. For example, the petrified forests. It's this material exactly. Now about methods to transfer organic molecules to a planet, you would have seen three very nice examples. Allende meteorite, one. The other is Murchison meteorite and Orgueil meteorite. Okay, here with me I have one additional, which is very similar, the Vuna meteorite, which is very similar to the Hayabusa samples, if you want to see it from close. But very, very little material because it's very, very expensive, absolutely very expensive. So these are primitive meteorites which are formed during the first period of our solar system, and they have trapped simple organics that are generally synthesized from processes taking place on the grains of interstellar medium and close to the suns of protoplanetary disks. You've heard already earlier how this is done. And now here you have methods to transfer water to a planet. You have two examples here. One meteorite from Vesta. The Vesta piece is this one down here. This is a small part of this larger piece, about 7 kilos, I think, is this meteorite. It's the Camel Donga achondrite eucrite, and it's a rock formed from the cooling of the 4 Vesta asteroid, which is a differentiated planetesimal, and at the asteroid belt between Mars and Jupiter. And differentiated means processes similar to the ones that formed the crust on Earth. And this, of course, concentrates the water on the surface of the planets. That's why they could transfer some water in other planets and form, like Earth, for example, and form the oceans here. And finally, you have the transfer of phosphorus to a planet. And here you have an example of an iron nickel meteorite, where you can see, if you go closer, and I have some pictures here, if you go to this area here and I zoom in here, you see this bright zone. This is schreibersite. This is a phosphoric mineral with this formula here, iron nickel, of course, plus phosphorus. And it is, since it contains phosphor, it could really provide the phosphor that life requires, as we already said. And at the end, you have some two new additions to this collection. One of them is black lava glass. This one you can see there. These are the latest discoveries for astrobiology for rover targets on Mars. These additions came after Bob attended the following meetings. From there, he took the idea and started to searching for such for these samples. You can see them here. This was about Mars extant life in New Mexico, and he was also landing. He was at the meeting for deciding on landing sites for the Perseverance rover in Los Angeles, and also he contributed there. So you see the black lava glass, which is a way. It helps in to produce with catalytic synthesis polyribonucleic acid on prebiotic rock classes from ribonucleoside 3 phosphates. Okay, and the salt. He was also a conference participant at Carlsbad in New Mexico, where it was highlighted for potential Martian refugium, says here. Yeah, it is places that life could form. These are and survive. These are caves, actually. We have to search for caves, and this is important. Deep subsurface, and it's supposed that the European rover has a drill to go to the deep subsurface, ices and salts. Salts are also found in the past in inclusions to keep alive bacteria that later on could be again become dormant if we open them up. So they are nice ways to really keep fossil life, actually not only fossil, but really to keep it, to preserve it in living form until now. And now, yes, the answer is the sun. I hope I really managed to say things as Bob would do. Thank you very much.